All right, welcome back everybody to Math 155, lab number 5. Today we'll be talking about derivatives, tangent lines, and we will determine when the graph of a function is increasing or decreasing visually. Um, Here we have two problems. Problem number 1, we will define a function. This problem is similar to the first two problems in the lab. Problem number 2 here is similar to problem number 3 in your lab. Today we will be learning a few new commands, especially with the command to take derivatives of maple. And we will be exploring some ideas that you should have been covering in your classes by now. Last week we saw what it meant for a function to be continuous. In your class you have been dealing with limits and limit computations. And the derivative arises from a limit computation. The derivative is a limiting process. So without further ado, let's just get started with the lab. So the first problem asks me to define a function f of x equals x squared plus x. So the first thing that I will do is I will define that function. I'll have f equals x squared plus x. But before I do that, this function is going to be eventually taking value, so I want to make sure that I tell Maple that the function is in fact going to be taking in values for x. So it's going to be x squared plus x. I am using the virtual console, so if you see some lag, that is the reason why. So now that I have defined my function, we will be approximating the line tangent to my function f when x equals 5, meaning when the input of f is 5, we'll try to find the tangent line at that particular point. To do this, we'll first find the equation of some other line, and this particular line will be the line passing through the points 1 and f of 1 and 5 of f of 5, where this coordinate pair, here the first coordinate is x and the value is 1, and the y coordinate is given by f of 1. If you remember from pre-calculus, whenever you plug into a function for x, the output will be y, because f of x equals y. Then we'll plot the graph, and we will do the same for 3 points of f of x that are very close to this particular point right here. In the lab, I believe I do this same thing again for the point given, but you don't have to because you already did it. Finally, we'll describe what happens to the slope of the lines. So let's get started with this. So first of all, to write the equation of a line, we have to remember a couple things. The first thing that we need to remember is that we need to know how to compute slope. So first, we need to know how to compute slope. Then we need to know how to write the equation of a line. Now, finding the slope and writing the equation of a line should not be new concepts. You have seen this in a college algebra class or any algebra class that you have taken before, and this was definitely covered in a pre-calculus class if you took pre-calculus before taking calculus. So these are not new concepts. To find the equation of the line, what you need to remember is the following equation. So what you need to remember is m equals y2 minus y1 divided by x2 minus x1. The difference in change of y divided by the change in x. And you also need to remember either the point intercept form of a line, which is y equals mx plus b, or the slope point form of a line, which is y minus y1 equals m times x minus x1. Here, y1 and x1 are any two arbitrary coordinates that are in the line, that fall on the line. So the first thing I want to do is, now that I have already defined what f is, well, let's find out what the outputs should be here for f1 and f5. So using Maple, I could simply do f of 1 and make sure that you're in math mode. So f of 1, that equals 2, and that makes sense because my original function is x squared plus x, and if x is 1, then 1 squared is 1, and plus 1 is 2. F of 5, on the other hand, will give me 30. And again, make sure that you are in math mode. So f of 5 should give me 30. I'm not sure, I keep falling into text mode. Alright, so now that we have these two values, we could begin to find the slope. So what is the slope? Well, the slope is the difference in y divided by the difference in x. So I have my two y values and I have my two x values up here. So I'm going to choose, you could choose any one of them to be x2 and y2. I'm going to choose 5f of 5 to be my x2 and my y2. So that means that 30 is going to be y2, and that forces 2 to be my y2. In turn, 5 becomes my x2, and 1 becomes my, not my x2, my x1, and 1 becomes my x1. When I do this, I get 7. So I have that the slope is 7. Now, since neither 2 or 3 are the y-intercepts because their x-coordinate is not 0, instead of using the point-intercept form, I'm going to use the slope point form of the line. And I'm just going to do one extra step. Instead of having that y1 on the left side, I'm going to add it to the right side. So I'm going to add on both sides y1. That makes the equation of the line looks like y equals mx plus b eventually, once you simplify. So what do we have here? I have y equals m, well, we have 7. Then x minus, well, what is x1? I could pick any of the 2 points. Again, these are arbitrary points. So I'm just going to pick x1 to be 1, which means that y1 is going to be 2, so plus 2. So the equation of the line is 7x minus 5. We can check that. If you fold, you get 7x minus 7 plus 2 is minus 5. So we could certainly do this. So now we have the equation of the line that goes through the point 1 and f of 1 and 5 of f of 5. Now the next thing is to plot that line with the graph of f of x. So we want to plot the line with f of x. And then we want to do the same thing, meaning the same process, with 3 points on the graph of f of x that are very close to 5 f of 5. So let's see what we get here. Now we have plot f of x, and then we have 7x minus 5. Again, from one of the previous labs, to plot two functions on the same graph, you have to put these brackets, the one that look like this, squirrely brackets, I guess. So let's first just plot them and see what they look like. If we notice, with the graph of f of x and the graph of 7x minus 5, the line is not a tangent line, it's a secant line. So this particular line does not give me a tangent line. So we have to keep on estimating and approximating values that will. So let's try to pick some other values close to f of x, to f of 5. So I'm going to see if the point, let me just write it, I'm going to see if the point 2 and f of 2 give me the desired result. So all I need to do is find out what f of 2 is. F of 2 happens to be 6, and again I have to do the computation for the equation of a line. So I already know that f of 5 is 30, and my x1 is my x2 is going to be 5. So I'm just going to keep using those values. So I have 30 minus 6, that's the difference in y, divided by, well, now I have 5 minus 2. Now I have that the slope, instead of being 7, now the slope is 8. So if I rewrite the equation of the line, now we'll have y equals 8x. And again, I could pick any of the 2 points. So I'm going to pick 2 and 6 because they're smaller. Minus 2, and then I have a minus 6 on top. But remember that negative 6 is from the formula. So this is actually a plus 6. So I get y equals 8x minus 10. So again, we will plot f of x and 8x minus 10. Whoops, I do not have the brackets. All right, so as you can see, now the distance here between the red line and the blue line became shorter. So we're getting there. We're not quite there, but we're getting there. So let's try again with the point 3 and f of 3. So I have 3 and f of 3. So once more, I will evaluate what f of 3 is. F of 3 in this case is 12. So to find the slope, we will do 30 minus 12 divided by 5 minus 3. Now the slope is 9. So now I get y equals 9 x minus, I mean again I could pick any of the 2 points, so I'll just pick 3 and 12. So x minus 3 plus 12. And I get y equals 9x minus 15. So let's again plot this. So I have plot f of x and 9x minus 15. And now it's looking like the tangent line. However, we still have to verify, so let's zoom in. I'm going to zoom in from 2 to 6. And as you could see, we are not quite there yet. We still have a secant line. To the naked eye, it looked like it was a tangent line, but it's not. We're getting closer. So let's try 4 and f of 4. So the next point that we're going to try is 4 and f of 4. Once more, we will evaluate what the value of 4 is in the original function. That happens to be 20. Then we'll find the slope. So the slope is going to be 30 minus 20 divided by 5 minus 4. And we get 10. So now we have that y equals 10 times x minus, and I'm going to use 4 and plus 20. So we get 10x minus 20. as the equation of the line. Now let's plot once more. So plot f of x and 10x minus 20. Now if you look at it again to the naked eye, this looks like the equation of the tangent line. But we know better than that, so let's try to zoom in. So let's zoom in, and I'm going to zoom in from 3 to 6. So from 3 to 6, it still looks like the equation of the tangent line, but if you notice here, it's not quite. So let's zoom in a little bit more. So let's go from 4 to 5.5. So as you can see, this is still not the tangent line. This still looks like a secant line. Let's see if I can zoom in a little bit closer from 4.5. You see? This line is coming over on the other side. So that's not quite what we are looking for. So I'll pick a point even closer to 5 and f of 5. So last number we picked was 4 and f of 4. So now I'll do 4.5 and f of 4.5. And I was in math mode, which I did not want to be in math mode. So let's try to get rid of this error. So the point that I'm using is now 4.5 and f of 4.5. All right, so let's determine what the value of the function is at 4.5. The value of the function at 4.5 is 24.75. So now let's find the slope between this point, and again I'm using the original point 5 and f of 5. So I have 30 minus 24.75 divided by 5 minus 4.5. So now I get the slope to be 10.5. So let's see what we get here. So we have f, actually plot f of x, and I could actually do this, but let me actually write the equation of the line. So the equation of the line is y equals 10.5 x minus 4.5 plus 24.75. So now I could do plot f of x, comma 10.5 minus 22.5. Don't forget your x's. And this is now really looking like the tangent line. So as we can see, the more that we have approximated, the closer we've gotten, the better our approximation has gotten. So now more and more we're looking like the tangent line. So let's just zoom in to see what we have. So x equals, I'll do 4 to 5.5. And this is definitely looks like the tangent line at 5. We could try to zoom in closer to see. Yeah, the closer I get, let's see, 5.4. Let's do 5.2. Let's do 4.7. Let's do 5.1. 4.8. So this is not the tangent line, as you see, the closer we've gotten, the more we see that this line is over the blue line and then comes across on the other side. But it's very, very close to being the equation of the tangent line. In fact, once you, if you take the derivative of the original function, x squared plus x, you will be able to tell what the actual equation of the line should be. But this is what I want you to do on problem number 1. We are doing estimations um, to approximate the tangent line for the given function. Now, we already did this for more than 3 points. We did it from 2 through 4.5, so that takes care of this. Now, I want you to describe what happens to the slope of these lines. So if you notice, we began with a slope of 7, then we began with a slope of 8, then we had a slope of 9, then 10, then 10.5. And if you notice, we are getting very close to a particular number. We're reaching a limit for a particular number. So can you figure out what the derivative of f of x is at x equals 5? Well, it will definitely look very close to this particular equation. In fact, if we take the derivative, if you do it by hand, from the things that you have learned in class, from the original equation again was, in fact, let me just write it. The original equation was x squared plus x. If we take the derivative of this, we should get 2x plus 1 by the power rule. So we bring down the 2, take 1 away from the exponent, and then the derivative of x is simply 1. So the derivative of f of x should be 2x plus 1. So let's call this f prime. So I'm going to call this f prime, and I'm going to define it as a new function. Cannot have prime on the argument on the left side. That's okay. So let's call this f1 instead of f prime. All right, so f1 is the derivative of f. It's the first derivative. So we get 2x plus 1. If I want to now figure out what the value of the derivative is at x equals 5, then I just plug in 5 for the derivative. By the eye test, you could see that it's going to be 11, because 2 times 5 is 10, plus 1 is indeed 11. But if you notice, our approximation was very close to 11. We had a slope of 10.5. And in fact, you could have continued this process of picking values close, very close to 5 and f of 5, and your approximation would have gotten even better. So I could have picked then, let's say, 4.9, and this would have looked very close or to 11. This 10.5 would have instead been very close to 11, which will have meant that our approximation would have been much better. In fact, it would have been almost perfect. So let's just plot f of x and its derivative, which I call f1 of x. See what the actual slope of the line looks like. Whoa. That's before we plot, let's write down the equation of the line that passes through the point 5 and f of 5. So the slope is 11, so I have y equals 11 x times x, and my point was 5 and 30, so minus 5 plus 30. So I have y equals 11x minus 25. So now I could plot f of x and the tangent line, which is 11x minus 25. Let's make sure that we put the brackets. And now we actually do get the equation of the tangent line. So when I zoom in now, let me zoom in from 4.7, as I did before, to 5.1. As you could see, these lines look identical at 5. I mean, there is no telling that one it's going over the other. So if I get closer, like a 5.9, they're basically the same line. Let's get even closer. So if you see, the closer I get, the more like a straight line this looks. And we know that it doesn't look like a straight line because our original function is a parabola. And that takes care of problems 1 and 2. So for problems 1 and 2, we're approximating the tangent line at a particular point. For problem number 2, we are asked to define a function h of x such that that equals x to the fifth minus 4x plus minus 4x cubed plus 1. Then we are told to define a of x to be the derivative of h of x. Then plot h of x on a graph and then visually determine where x is increasing and where x is decreasing. Then finally plot a of x and visually determine where x is positive and where x is negative. And finally discuss the relationship between a of x and h of x and how they increase or decrease. So let's take this step by step. Step number 1 will be to define the actual function. So I'm defining a function h of x. So let me actually just bring this down. So I have it down here. So I'm defining a function h of x. So that means that h, make sure that you are in math mode. I am right now, not in math mode. Now I am. So I have h equals x to the fifth minus 4x cubed plus 1. So I've defined the function h. Then I am told to define a of x to be the derivative of h of x. So you could try to do this by hand, and that's fine, but that is not the point of this class. The point of this class is not to be doing things by hand. It's to use the technology available to us. Now, one thing that you could do, you could come here to expression, and you could go d dx of f, and you'll find that you could take the derivative. Or you could simply use the differentiate command. So to use the differentiate command and take derivatives, all you have to do is type diff, open parentheses, and then the expression that you want to differentiate and the variable that you want to differentiate in respect with. So we could do the following. I have x to the fifth minus 4x cubed plus 1. Notice that I get an error because I did not specify the variable, so comma x. So we are differentiating with respect to x, so I have to put a comma and an x. If this were y, then I would be putting comma y. So I now know that the derivative of h is 5x to the 4 minus 12x squared. In fact, I could do something even better than that. I could say that I could have defined it up here, but I'm going to define it down here. I have that a is what we have up there. So I have 5x to the 4 minus 12x squared. So now I have defined a function h and a function a. Now we are told to plot h of x on a graph and then determine where x is increasing and decreasing. So let's plot h. So plot h. By the naked eye, you could assume that, well, from pre-calc, you know that you read a graph on the Cartesian plane from left to right. So from left to right, this is increasing, then it goes flat, and then keeps on increasing again on the right side. Now you have to be careful. You have to actually try to see what's happening here on this mid portion. Because as you see on the y-axis, this function is increasing so quickly that we go from 0 to 20,000 very quickly. In fact, extremely quickly. So we want to make sure that we zoom in to see that we are not missing anything. So I'm going to zoom in from -5 to 5 to see what we have. Okay, so from -5 to 5, this still looks flat. Let's go from -4 to 4. Now, if you notice, there's a little bump here and a little portion that's going down here. So let's go -3 to 2, in fact. And bingo. So now we could clearly see that from -infinity to whatever point this is, we are increasing. Then from this point to whatever point we have here, we are decreasing. And then from this point onwards, we are increasing. So if you wanted to actually figure out what point those are, we'll get even closer. So it looks like about -1.7 is when you begin to decrease. So we could say from -infinity to -1.7, the function or x is increasing. So you could say so the function values are, the function is increasing up to this point. Now, from that point on, so between -1.7 and let's see on the other side, so we're very close to 2, so I'll do 1 and 2. All right. Now on this other side we have roughly 1.6. So between -1.7 and 1.6, the function is decreasing. And from 1.6 to infinity, the function is increasing, that we saw from before. When I zoom out again, you will see that that is the case. If I go from -5 to 5 once more, you will see that from whatever point on, this continues to go up. So we answer that part. We now know from which part to what part the function x is increasing and decreasing. Now, let's talk about the derivative. So we're going to plot a of x and make sure again that you're in math mode. So plot a of x. And again, this looks like it's increasing from 0 to infinity and it's decreasing from -infinity to 0. But looks can be very deceiving. So let's try to zoom in. So I'm going to go from x equals -4 to 4. So x equals -4 to 4. So here we see that there is definitely some negative values. So let's zoom in even closer. So I'm going to go in from -2 to 2. There we go. So now this looks very smooth. So we could clearly tell that the values are negative from -infinity to whatever point this is, and they're positive from that point to 0. Then they become negative again from 0 to this point, and then finally positive again. This is actually very important. This is the derivative of this graph. Keep that in mind. This graph is the graph of the derivative of this function. So let me make sure that I'm in text mode. By the looks of it, from negative infinity to, let's call that negative 1.3. I'm just too lazy to zoom in. The graph is decreasing. And when I say the graph, I mean the graph of a of x. And then from minus 1.3 to 0, the graph is increasing. And again, I'm not using set notation, so if we were using set notation, then we could speak about open versus closed intervals and so on, but I'm avoiding set notation for now. So yeah, so the graph is increasing from 0 to roughly 1.3, let's say. So from 0 to 1.3, the graph is decreasing. And you can see it from here to here, you went down. And finally, from 1.3 to plus infinity, the graph is increasing. And the question really is, why is this happening? What is the relationship between a of x and how h of x increases or decreases? Well, you will learn soon enough in your class, if you haven't already, that the derivative at a particular point tells you whether the original function at that particular point is increasing or decreasing. For instance, if I took a of x and I made x be equal to negative 1, then I have negative 7. What this means is that on the original function, you are decreasing at the point x equals negative 1. So let's go back to the original function. Let's go from minus 2 to 0 and let's see if this is true. Well, this is indeed true. So we are decreasing at negative 1. If I checked, let's say, for 3, I get 297. 297 is a positive number. On the original function at 3, I will be increasing because I had a positive number. So let me zoom in from 2 to 3.5. And as you can see, at 3, I am increasing. The function is increasing. So this is the takeaway of this portion of the class. The derivative helps you identify when your function is increasing or decreasing. And as you will see in the future as well, it will tell you whenever you have a change in direction. I will leave it to your lecture professor to actually define what that is for you and what the name of it is. For the time being, however, this is what you have to do for this particular lab. Finally, the last thing that you need to do again is to save. I want this saved as a PDF. So to save as a PDF from either the virtual console or from just regular Maple, you click File, you click Print, and you change it from Microsoft XPS to Foxit Reader PDF. You click OK. Then you name it. So I'll name it Lab 5. And I save it. And finally, you go onto Blackboard and either you upload your work, or what I prefer is that you email yourself the work so you have a copy of it and then upload it to Blackboard. That is it for lab 5. Thank you for your time.